Hi guys, this is our first video series for lecture of Chem 112 for the spring semester. We're going to begin with a quick review, and then we're going to abandon this lecture for a little bit. We'll come back later, so don't worry about it, but we have to cover chapter 12 before we can jump into chapter 13. So for this, you want to go ahead and go to the lecture notes online on Blackboard and print off the one that says review and chapter 13.1 through 13.4. Now you're actually going to bring these to class, so you need to make sure you've printed it before you start the rest of this lecture so you can fill it in as you go. You get credit for doing the lecture portion at home, so make sure that you've printed it. Alright, so the first thing I want to discuss is this figure that I've made for you. It helps you to envision how you used stoichiometry in Chem 111. So let's say, for example, that I know how many grams I have of sample, and I ultimately want to find out how many. Okay, so if we want to get to atoms from grams, so this is sort of where we want to end our calculation, there's going to have to be 3 conversions. The first one is going to use the molar mass to go from grams to moles. So basically you're putting grams on the bottom there. So it would be moles on top, grams on the bottom. So if I multiply the grams I start with by sort of the inverse of molar mass, then of course we can cancel the grams. That leads us to moles in this box. From there, I can use Avogadro's number, which is spelled out right up here. But it's pretty much this value flipped over. So you're going to multiply the number of moles by 6.022 times 10 to the 23 molecules per mole. That cancels the moles and gets you into terms of molecules. So now we're in the third box. Then I look at the chemical formula and I use the subscript for that particular element to figure out the relationship between that element and the total molecule. So for example, if I was looking at H2O, and I want to know how many hydrogen atoms I have in a given mass of H2O, then all I have to do at the last step is multiply 2H for every 1 H2O. So that's the ratio. And that gets us to total atoms, okay? So this kind of graphic is helpful while you're doing your homework and reviewing some things. This helps us remember the facts that we already know and the relationships we can use to go from one factor to another. When we do this, the key strategy in terms of the math is called dimensional analysis or factor labeling. That's the thing where we write all the units and they better cancel if it's done properly. Alright, so in that vein, if we wanted to go, here it says how many moles of ammonium chloride are present in 4.5 grams of sample. So what I'm doing is we're going from moles is our ultimate destination, and we're trying to start at mass. So that means there's one conversion to go from mass to moles. The first thing we need to know, though, is what is ammonium chloride. And so on the back of the periodic table that I provided, you'll find a list of polyatomic ions. And the first one on the list, because it's sort of alphabetical, is ammonium. And it says the formula for ammonium is NH4+. And then we think, okay, so the other part of this compound is chloride, and chloride means chlorine with a negative charge. So if ammonium is +1 and chlorine is -1, when I make these into a compound, then it's going to have the formula NH4Cl. So that's what ammonium chloride is. Now, if I have 4.5 grams of the stuff, then that's my starting point. So I'm going to write that down. Okay. Let's see here. I got some space. So 4.5 grams of NH4Cl is where we're starting, and I'm going to multiply it by molar mass, but I want to put the grams on the bottom. I'm going to put moles on top because ultimately that's where I'm trying to get. And so to figure out how many grams for 1 mole, I have to add them up from the periodic table. Okay, so all I do is I look up the mass of nitrogen on the periodic table and hydrogen, and of course there's 4 of them, so I'm going to multiply that, and chlorine, and then we add those all together to get the total molar mass. Okay, so molar mass always has the units grams per mole, and it always comes from the periodic table. So since I'm starting with grams here, and I want to cancel it, that means that this unit grams is going to go on the bottom, and this number, 53.5, is stuck with it. Okay, so we're going to put that on the bottom of our fraction here. That means that the grams here and the grams here are going to cancel because they're on opposite sides of the multiplication, and that leaves our unit as moles. Okay, so what I'm actually going to put in the calculator is 4.5 divided by, because this is on the denominator, 53.5, and when we hit equals, we get 0.08411121 and a bunch of other numbers. My initial data only had 2 significant figures, so my answer is also going to have 2 significant figures. The zeros do not count because they're not after an integer, so we're just going to write 0.084 moles. Okay, so a couple things here. Using molar mass as a conversion factor, if you want grams to be canceled, it goes on the bottom. If you wanted moles to be canceled, you just flip that over. You get molar mass from the periodic table, and we always need to remember to check significant figures and make sure our answer has a unit. Okay, so the next one is relating the amount of one substance to the amount of any other substance in a reaction. So we call that process the mole ratio. But it works similarly because we're still going to use dimensional analysis, which I like to abbreviate as DA. And the difference is that the fraction we're going to use is not the mole ratio. It comes from the coefficients of a balanced reaction, so the numbers in front of each compound. So for example, if we have 5 moles of KClO3, I want you to give a shot at naming this, by the way, and I'll give you just one hint. The polyatomics on the back of your periodic table might be helpful there. So we're going to take 5 moles of that KClO3, and we want to figure out how much O2 there is. So that means I want to keep O2, and I want to get rid of KClO3. The numbers to put in front of those come from our balanced reaction. So it says there's 3 O2, and let's see, KClO3 has 2, so we're going to put these numbers there. So what I'm going to enter into my calculator is going to be 5 times 3, so that's 15, and then divided by 2, so we're going to get 7.5, and our unit is still a mole, but now KClO3 has canceled, so we're left with O2. Okay, so that's the molar ratio. That's how you go from the amount of one substance to the amount of anything else. We could have also done the same thing to figure out how much KCl was present, or if you know O2, to find out any of the other ones. So if we have 7.5 moles of O2 and we want to know how many grams that is, we can go back to our chart to help us figure out how to do that. So we're going from moles here. Let me just clean this up a bit. We're going from moles into mass, so therefore we're kind of going this way. So that means I want to use the molar mass again, but this time I want to put grams on top because that's the answer I'm trying to get to. So 7.5 moles O2 times the total mass of this compound. And so I look at the periodic table and I find that the mass of oxygen is 16 grams per mole, but there's 2 of them, so that would be 32 grams per mole. And here I'm putting moles on the bottom so I can cancel the mole I started with. Okay, so I'm going to enter 7.5 times 32 grams into my calculator. I only have 2 significant figures, so we're going to just keep the 2 there. And so the answer is 240 grams. This 0 is not significant because there's no decimal point after it, so I'm just going to leave it that way. And then the next question is, how many grams of KClO3 did we start with? And the answer to that is obtained doing the same exact thing. So I want you to do it on your own. I want you to calculate the molar mass, show all your work for that. And then I want you to convert from moles into grams. Okay, so I've shown you a couple of examples of that, so do that on your own. Of course, you can pause the video to do that. All right, so the next part we're going to review is about Lewis structures. So when we're doing Lewis structures, the thing we're interested in is valence electrons, which is just a fancy way of saying the outer electrons. So you should review how to count valence electrons if you don't recall. The best tool for that is the periodic table itself. The key to writing a good Lewis structure is that everything wants 8 electrons. That's what's stable. So everything is going to react to try and get 8 electrons. So for example, if I have the element magnesium in my compound, I know that's a metal because it's on the left side of the periodic table. It's in group 2 actually. So that means that I also know it has 2 electrons in the valence shell. And then this says I have 2 chlorine atoms, so I'm going to draw 2 individual separate chlorines. That's what the subscript means. And chlorine is in group 17, so that means there's 7 valence electrons. So when I fill these in, I'm going to choose to do 1 on each side until it's full like this, and then I start to pair them up. So 7 valence electrons for both. So these are the elements that are participating in the compound. Now I know this is an ionic compound because it's composed of a metal and a non-metal. And I know that ionic compounds have a tendency to give up their electrons from the metal to the non-metal. So we're not going to draw this as shared electrons. This has to be drawn as electrons being completely given from the metal to the non-metal. And we said that everything wants 8 electrons, so since each of these chlorines starts out with 7, that means that each one of them is going to take an electron from that magnesium. Okay, so if that happens, then our final product, which I'm going to draw here in purple, is going to be magnesium where it has lost 2 negative charges. So that leaves behind 2 extra protons, or a charge of 2+. And we also are going to have 2 chlorine ions where there are 8 electrons, and so since each one of them absorbed 1 electron, that means that chlorine has a negative charge, or rather both chlorines have a negative charge. Alright, so that's how we draw the Lewis structure for an ionic compound. When we do covalent ones, these rules work better. Basically, you put the element that belongs in the center. By the way, this is usually the first element written in the compound. So, for example, in the compound carbon dioxide, carbon is in the center. So I'm going to write that one in the center first. And then the oxygen's on the outside of that. I place the number of valence electrons around each element that they have as elements, and then I try to connect them so everybody gets 8. There's a few patterns that you can learn to recognize that you probably should know. For example, carbon always needs 4 electrons because its element has 4 already, so it's looking for 4 bonds. Oxygen is in group 16, so it has 6 valence electrons, which means for it to be happy, it's got to absorb 2 electrons from somewhere. So that means oxygen is looking for 2 bonds, so that kind of stuff. We can make single bonds by doing 2 dots between the 2 elements like this, or you can do it as a line. The line means 2 electrons. Double bonds, similarly, are represented with 2 lines or with 4 dots. Either way you want to do it is fine with me. Alright, so I'm only going to choose to do methane, CH4, and then I want you to practice the other 3. So we said that the central atom is carbon, and it has 4. Okay, So this is what you get.